Hey everyone, this is me a video walkthrough of problem 5 on CS61B Spring 2020, the final. Let's get started. So we'll walk through all parts in this video, and let's start off with part A. So part A reads, consider the following algorithm on a directed acyclic graph G. So we have some algorithm tsort, and I think it's helpful to try to understand what tsort does before we actually dive in to these multiple choice questions. Okay, so I think the best way of trying to understand how some sort of algorithm works is to maybe just run the algorithm on an example graph. So let's say that we have some example graph. Let's see. Okay, I'm just going to quickly create a graph. So notice here that what I created is the graph is directed because it has directed edges. It's acyclic. Notice that this graph has no cycles. From any vertex, I can't get back to that vertex. That's not possible, right? So I created some directed acyclic graph G, and now let's just see what happens when I call tsort on G, okay? So if I call tsort on G, it's going to begin up here, start with all vertices of G being unmarked. So let's maybe highlight a vertex in yellow to mark it. And then it says we have some output, which is some empty list. So let me create that at the top. Okay, so output is some empty list. Then the next thing that happens is that we have some while loop here. While there are unmarked vertices in G, we're going to let X be some unmarked vertex, and we're going to call traverse on X. All right, so it seems like X is any unmarked vertex. So let's just, for the sake of an example, let's just choose B. All right, so what I'm going to do on this left-hand side is kind of keep track of these recursive calls. So we're going to be calling traverse on B. Then maybe just to make it a little more succinct, let's just make T of B denote traverse of B. Okay, so T of B is just a short form for traverse on B. All right, so when I call traverse on B, what happens is that we see that B isn't marked, so we're going to mark it. Then what we're going to do is we look at each edge, and then we call traverse on that. So we have kind of two edges here. So let's just choose one of them arbitrarily. Let's choose D. All right, so from T of B, we then call T of D, right? Because that's what we're going to call traverse on G, D, and output. We're going to see that D is not marked, so we're going to mark it. Then what we're going to do is we're going to look at each outgoing edge. Well, there aren't any outgoing edges, so then we're going to append D to the end of our output, right? So D is the first thing we kind of put in our output here. So then we're going to conclude the recursive call to D. We'll kind of come back up to B, and then we will call traverse on A, right? So we call traverse on A, we see, hey, is A marked? No, it's not, so we'll mark it. Then what we'll do is we'll consider like each outgoing edge, right, which is just this edge right here. So then what we'll do is we'll call traverse on D, right? Well, after calling traverse on D, we see D is marked, so nothing really happens. So then we kind of come back up to the recursive call for A. So notice that this is the only outgoing edge for A. So we exit this for loop, we'll append A to the end of our output, and then we'll return back to the function call for B. And then now that we've visited all the neighborhoods of B, we'll terminate. So now we're going to kind of come back up to this while loop. So while there's unmarked vertices in G, notice that they are unmarked vertices. These are all unmarked. So let's just randomly choose an unmarked vertex. Let's say I chose G. Then we'll call traverse on G, right? So after calling traverse on G, we'll see G wasn't marked, so then I just marked it right now. Then we look at each edge. There are no outgoing edges, so I'll append G here. Then let's say I call traverse. Let's say we come back up from this while loop, and then I say X is equal to F. So I call traverse on F, I mark it, right? And then we can kind of see here that we've already looked at like its only neighbor, G, so we're not gonna do anything else. Then maybe let's say I call traverse on C. So I mark it, I recurse on B and E. We see B isn't marked, so we don't do anything. When I recurse on E, then we'll mark E and add E to our output. And then finally, we'll add C to our output. And I forgot to add B to our output. That's the only thing. Nope, shoot. I think B should have gone right here. Right? Okay. So now that we kind of understand like how this algorithm works, let's look at these questions here. So I think maybe let's start off by looking at these two questions here. This part claims that some vertices might be excluded, and this one says some vertices might be added multiple times. So I'm going to claim that both of these are false. And the reasoning is every vertex is visited exactly once. Okay, and the reason I'm making this claim is because of how we've constructed this if statement here. So notice in this if statement that no vertex can be visited more than once. Okay, so what I'm denoting visiting is I kind of like maybe add X to my output, right? Well, let's kind of think about why it's the case that no vertex can be visited more than once. Well, if it's the case that we haven't been to X before, right, then X won't be marked and we'll mark it, right? Then if we ever call traverse on that vertex we've already been to, I kind of recall here that we called traverse on D even though we've already been there. Since X is now marked, or in our case, D is marked, then we won't enter this if statement ever again. So what the claim is that we'll enter this if statement exactly once for every vertex. And why is it the case that every vertex will eventually enter this if statement? Well, that's true because if we're looking at this while loop here, notice that if X is an unmarked vertex, we're going to call traverse on it. So we're going to call traverse on every unmarked vertex until there's no more unmarked vertices. That's why this if statement will go inside this if statement exactly once for every vertex in the graph. That's why both of these are false. So now let's maybe come up here and let's consider this top one, which is T sort returns a correct topological sort of G. So this is false as well. It actually returns the reverse. Okay, so let's maybe see why it returns the reverse. If you're looking at this example here, notice that if I maybe connect all the vertices with edges like B to D, A to D, F to G, E to B, C to E, I think I got an B to D. Right? If you notice, all of the edges between these vertices kind of go in backwards order. So it's not a valid topological sort. It's rather the return of the topological sort, the reverse of the topological sort. So what we'll see here is that that implies that this last one is true. So some vertices in output precede them in a topological sort. Well, since it's the reverse, this one makes sense. And then finally, I'm also going to claim that this one is also true. The reason that this one is true is because of the fact that every edge is considered once and exactly once, okay? The reason is that if every vertex is visited exactly once, that means every edge is also visited exactly once, because every time we go to some vertex, we consider each of their outgoing edges. So since it's a directed graph, every edge will be considered exactly once, right? So T sort will take theta of E time. Nice, let's move